Okay, AP Physics, student workbook 3N, Newton's Law of Universal Gravitation. We're going to work through this nice and slow. This one can get a little bit heavy, so we're just going to work through it piece by piece. The scenario says as follows. A student is given the following set of orbital data for some of Jupiter's moons and is asked to use the data to determine the mass m1 of Jupiter. Assume that the orbits of these moons are circular. It gives us the orbital period t in seconds, and it gives us the orbital radius r in meters. And it looks like the first thing that it wants us to do is it wants us to calculate s squared, which is seconds squared, and then it wants us to calculate meters cubed, which is then going to be meters cubed. This entire thing reeks of Kepler's laws because there's a relationship between the period squared and the distance between the two objects cubed. So it looks like it's going to make us crunch this data. So I think the first thing that we need to do is take our calculators and wait, this isn't a calculator. Wait. All right, so these numbers are way too big for a cell phone, so I hope to God that you guys are actually going to use something besides that. Get yourself any calculator that can handle this scientific notation better than a calculator. And some of you guys will use a calculator anyway from your cell phone, and you're running your own risk whenever you do that. I like having this little fancy button that says EE. That's an automatic times 10 to the power, and it just makes our life a whole lot easier. So we're going to go through those, and this is good practice to make sure that you can actually type in these numbers before you get to the AP Physics exam and go, oh my gosh, I don't know how to use a calculator, which happens to quite a few people. So we're going to go ahead and calculate some of these things. The orbital period, 2.08 times 10 to the second. I'm going to type in 2.08. EE stands for times 10. I can't even do it right. 2.08 EE, and then that's the seventh power. So 2.88 E7 comes out to that number. And then I'm going to square it because I have to take that number and square it. So that comes out to, I don't want to type in, or I don't want to write 4.3264 E14 times 10 to the 14th power, because if I do that, that's just a lot of digits. We have 3 sig figs in the problem to start with, so why don't we just end with 3 sig figs? So we're going to call this first one 4.33 times 10 to the 14th power. So we're going to write down 4.33 times 10 to the 14th. And we know we're in seconds squared, so we'll just go ahead and keep that up there. Also, keep in mind that exponents add when you multiply them, so a good way to double check yourself and make sure that you've actually done it okay in the calculator is 7 plus 7 would actually come out to be 14. So as long as you're close to that in the addition, you should be okay. All right, so then the next one is going to be 2.49 times 10 to the 7th power, and 2.49 times 10 to the 7th power is that number, and then I'm going to hit caret 2 to square it, and that comes out to 6.20 times 10 to the 14th power. So 6.20 times 10 to the 14th power. Next one, 4.05 EE, 7. I'm going to go ahead and square it, raised to the second power. That comes out to 1.64 times 10 to the 15th power. So I'm going to write out 1.64 times 10 to the 15th. 64 times 10 to the 15th power. And then last but not least is 5.04 EE, 7th power. And then I'm going to hit caret 2 to square it, and that comes out to 2.5 times 10 to the 15th power. Okay, so 2.5 times 10 to the 15th power. Another reason not to use your cell phones is you're not allowed them on the AP Physics exam, so why would you try to use them now? You know, convenience would be one, and I get that. That's not a big deal. All right, so let's look over here at meters cubed. I have to take the orbital radius in meters, and I have to cube it. So it's going to be the same exercise. So we're going to do 1.12 to EE, 10th power, and then I'm going to take that number and raise it caret 3. So I'm going to raise it to the 3rd power, and that gives me 1.40 times 10 to the 30th power. And next one in line is going to be 1.26 times 10 to the 10th, so 1.26 EE, 10th power. Hit enter, and then raise it to the 3rd power. That comes out to 2 on the dot, 2.00, you know, within a margin of error. 2.00 times 10 to the 30th power. Let's see here. Next one in line is 1.71 times 10 to the 10th power. So 1.71 EE 10. And then that's going to be caret 3, raises it up to the power. So you get 5 on the dot. Ooh, so nice. So it comes out to be 5.00 times 10 to the 30th power. And then last but not least, we're going to do 2.02 times 10 to the 10th power. And then we're going to do caret 3. So that's going to raise it to the third power. And that gives you 8.24 times 10 to the 30th power. So we're going to go 8.24 times 10 to the 30th power. All right, well, we at least have our data right now, so that's good. Next thing in line is it says create or write an algebraic expression for the gravitational force between Jupiter and one of its moons, any one of its moons. It says that up in the top that it wants us to use M1 for the mass of Jupiter, so I guess we better use big M1 for the, or is that J? Is that a J? Yeah, big MJ for the mass of Jupiter, so I guess we'll use that. Let's see here, between Jupiter and one of its moons. Let's see here. Let's see, force of gravity. Oh, I know. So from the formula sheet, we can use the force of gravity is going to be equal to big G, gravitational constant, times the little mass of the moon, times big MJ, divided by the distance between them squared, r squared. Now, I think it says that oh yeah, look down here. It says that it wants us to use an orbital period of t and a radius of r. I'm getting ahead of myself though, but that is that Fg is the force of gravity between the two planets, given the distance between the Jupiter and its moon. The moon will be little m, and the mass of Jupiter will be big M. Now, in part B, it says use your expression from part A and the assumption of circular orbits to derive an equation for the orbital period t of a moon as a function of the orbital radius r. Now, here's where it gets interesting. Now, remember, keep in mind on the right side, we have to explain what we're doing, and then on the left side, we have to actually write the derivation. So, whenever we derive, and it did say derive, so we do have to derive an expression. We're going to have to start with something on the formula sheet, and we have to use that on the formula sheet to create a workable expression. So on the formula sheet, what we have is we have the force of gravity is going to be equal to big G. Let's write what we just wrote up here. The mass of Jupiter times the little moon divided by the radius squared. That's the force of attraction between the two. Oh, I better use big R. It said to use big R in the formula. So here's big R. And we'll have big T later for the period of revolution around the object itself. Okay, so what is this? You could call this Newton's second law, or you could call this the sum of the forces. Either way is perfectly fine, but what we're doing is we're relating the force between two objects. Also, you could say that it's universal gravitation. All of these are fine. Universal gravitation between two objects. Okay, these are good justifications. Now, on the next part, what we need to do is we need to say, okay, well, if this is going around in a circle around the object, so if we have something undergoing uniform circular motion, then there's something keeping it in the circle. And in this case, the force that's keeping it in the circle, the centripetal force here, is the force of gravity between the two objects, that gmm over r squared. So what we're going to say is we're going to say that, okay, well, this G mass of Jupiter, big J, times the mass of the moon over the radius squared is going to be equal to the centripetal force that is the centripetal force going around the object. So we're going to put the little mass of the moon times the velocity squared divided by the distance between the two objects, because centripetal force is defined as being the mass times the velocity squared divided by the radius. So that's mv squared over r. And what we're going to say here is that we're going to say that gravity is the centripetal force, or gravity, yeah, we'll go ahead and say gravity is, because remember, centripetal force isn't really a force by itself. Things can be centripetal or they can be linear, but you can't just have like a centripetal force. Gravity is the centripetal force. It's a flavor. Gravity is the centripetal force. Let's make sure that we spell it right. Don't spell it as centrifugal because then I'll have to find you and hit you with a broom or something. It'll be centripetal force between the two objects. Here we go. All right, and you could probably come up with a couple of other justifications too if you wanted to. Now, to make our life easier down the road, let's go ahead and cancel out a couple of things that will cancel out eventually. So the mass of the moon is on both sides, and since everybody brought the mass of the moon to the party, we can get rid of both of those. We can also get rid of one of the big R's, and we can get rid of one of the squareds over here, so that we're just left with the velocity squared. And this will make solving our equation a little bit easier. So let's go ahead and write what's left over. So G times the mass of Jupiter divided by just one of the radius and not the other is equal to the velocity squared. So what did we do? We canceled out like terms. Or you could just say that we canceled the mass of the moon and the radius. If you're more of a math teacher person, then you could say that they canceled out like terms, and that would work out just fine. All right, now next in line, what we need to do is we know that the velocity going around a planet is uniform, so it's covering the circumference of that circle over a certain period. Now, in real life, it's a little bit elongated. There's a little bit of eccentricity there, or a little bit of an oval in the orbit, but it's close enough that we're just going to say, you know what, it's just a circular orbit, and it's within some kind of margin of error. Okay, so we're going to take this velocity and we're going to say, well, that velocity is going to be equal to 2 pi r over t. So I'm going to just say that, we know for a fact that the velocity around a circle is the circumference divided by the time that it takes to go around that entire circle. So I'm going to go ahead and square that. 2 squared is 4. Pi squared is pi squared. And the radius, or the distance between the two, is going to be r squared. The bottom, the time, will also be time squared, and that's going to be equal to big G times the mass of Jupiter divided by the radius between them. Now, if you're in my class, we've done this derivation before several times, so it shouldn't be new magic to you, but if you don't have me for class, this might be a derivation that you haven't seen before, so it's worth going over. Plus, it's actually in the workbook, so it seems like it's worth it. It seems to pop up on every single AP Physics exam somewhere in some fashion. It may not necessarily be a strict derivation, but it usually shows up. So what did we do? We substituted 2 pi r over t for velocity. Okay, and then the next thing that we need to do is, let's see, what are we trying to do? We're trying to find the orbital period t. So what we're going to do is we're going to move everything over that we can. So I'm going to take g and move it to the other side. I'm going to take r and move it to the other side. So the mass of Jupiter, I don't want to do too many things at once because then it just gets all crazy. That's going to be 4 pi squared. The r goes up here, so it's going to be r cubed. The g goes down here, so it's going to be gt, capital T squared for the time. Okay. So what do? We just rearrange some variables. We didn't really do anything physics-wise. This was a strict math step. And then the last thing that we do is we want to get the time and we want to get it to move over here. So we're going to take this time squared, we're going to move it to the top. We're going to take the mass of Jupiter and we're going to move it down to the bottom. So time squared is going to be equal to 4 pi squared radius cubed divided by g times the mass of Jupiter. There we go. And let's see, that's what we're going to do. I think that's the last thing that we did was we solved for t squared. Okay, and that will derive you an equation for the orbital period t of the moon as a function of radius r. If you want to take the square root of both sides to just find it as t is equal to the square root of everything else, you can do that as well. However, if you have it just like this, then it will be acceptable because you've solved for one variable. And usually whenever you graph these, if there's a squared and like a cubed, normally you're going to need those for writing out your graph to make it linear anyway. Speaking of which, it says in the next part down here, which of the following, let's see, ooh, there we go. Which quantities should be graphed to yield a straight line whose slope could be used to determine the mass of Jupiter? Okay, so what we would need to do in order to be able to find the mass of Jupiter is we would have to graph two things that are the data is related to each other. So the big thing that the data is related to here is the time and the radius between the two. So what quantities would we need to graph? We would need to graph t squared, and we would also need to graph the radius cubed. Okay, now the deal is which one should go where? So if we were to make like a graph of it, what should we put on which side? So if we were to make a quick little chart here, then on that chart, the way that you would want to have it set up is we would want t squared over here, and then we would want r cubed down here on the bottom. Okay, in the way that we have it set up in this formula up here. So if you think about it as if it was like y equals some other thing times x, the y value, or the value that would go up and down here, the dependent variable would be the time, and the independent variable would be the distance between the two objects. So if we change the distance between the two objects, that should change the orbital time between the two. So what we want to do is we want to have t on the y-axis, and then we want to have r cubed on the x-axis. And what that should do is that should allow us to linearize our values. Since this one is on top and this one is also on top, that would give us some kind of straight line value, which I have a funny feeling that we're actually going to end up needing to do. Let's switch over to the next page because there's another part to this. Oh God, there's a graph. Yep, it's totally asking us to do it. The real deal is here. It's getting ready to happen. So, what's it say? It says, complete the table by calculating the two quantities to be graphed. Label the top of each column, including units. I think we totally already did that in the columns above, whenever we wrote those numbers in. And it said, plot the graph on the axis below. And let's see here if I've got the other side to this. Plot the graph on the axis below. Label the axis with the variables used and the appropriate numbers used to indicate the scale. Okay, so it looks like it gave us to us, and here's radius cubed, and all of these are going to be like times 10 to the 30th, so that was already nice of them to give that to us. And then over here, the period squared is over on this side, and every one of those is times 10 to the 14th. So we can look at our data that we've got from the columns before, and we can graph these two columns that we have for our period squared and our distance, our radius cubed. So we're going to do that, okay? And we're going to get some values from this as we continue to move those up. So the first one that we have is the y value is going to be like 4.33, and the x value is going to be like, let's see here, 1.4 times 10 to the 30th. Okay, let's see here. That's going to put us, if we've got 4.33 times 10 to the 14th, that puts us about right here, and 1.44 times, and we can definitely kind of easily approximate here. It doesn't have to be, obviously, it doesn't have to be exactly on it. So this is going to be like a little bit before, so it's going to kind of give this dot like this. Okay, the next one is 2 times 10 to the 30th and 6.2. So at least here's a 2, and that'll give us 6, which is a little bit higher. I think each one of these squares is 1, 6, 7, 8, 9, 10, totally is. So that's going to give us like right here. The next one is roughly about 5 times 10 to the 30th, and that gives us 1.6 times 10 to the 15th. So we can think of that as like 16 times 10 to the 14th. So if we go up to 5, that should give us somewhere around 16-ish. Okay, and then if we go to, let's see here, 8.24 times 10 to the 30th, let's just go like a little bit over 8. And then for the value up, it's 2.5 times 10 to the 15th. That's like 25 times 10 to the 15th. So that's going to be like way up there. 2, 3, 4, 5. That's going to be like at the very, very top. So let's go 8.2. Let's go about right here. All right, and then what we're looking for is we're looking to see if these are actually going to come out to be straight lines, and it looks reasonable. Let's take a sheet of paper and use that as a straight edge. Hopefully you guys have a ruler. I'm apparently not as nice. Make sure that whenever you make your straight line between it, that you try to hug as many points as you possibly can for your line of best fit. And more importantly, you also, since this is some kind of relationship in linear, you want it to start at 0, 0, and you want it to work its way upwards. So we're going to just kind of make this line. And remember, it doesn't have to go through every point. I have one that's like a little bit off, and that's perfectly fine. No big deal there. But you can see that there's like a linear relationship. And a good way to tell that if you've got a straight line or a linear relationship is if you've got roughly the same amount of dots above the curve as you have below the curve as well too. So I see two of them that lie pretty much straight on it, and then I see this one's a little bit above, and then I see that this one is like a little bit below. So I've got one above, one below. Pretty good chance that this is going to be a linear value or a straight line. So let's see here. Is there anything else that it told us to do? I think it just told us to plot it. Yeah, calculate the table, label the top of each column, which it did. Oh, that should be on the previous page where our data is. Let's see here. Plot the graph on the axis below, label the axis with the variables used, and they already did it, and appropriate numbers, which they already did. Okay, so looks like all we had to really do was just make it linear to kind of graph it out. Okay, so part F, the next part says, two identical probes are sent to study one of Jupiter's moons. Probe A is in geosynchronous orbit. What geosynchronous orbit means to us is that one revolution, so one spin around the planet, is the same thing as one rotation. So, like for example, if a satellite was in geosynchronous orbit around the Earth, then that would mean that one orbit around the Earth on top, like one orbit, would be equal to 1 day, 24 hours, because the Earth rotates roughly about 24 hours per day. So therefore, one revolution around it or one orbit around it would have to be roughly about 24 hours as well too. So that's what it means whenever it says geosynchronous, is they're wanting it to stay put in sync with the rotation of Jupiter's moon. Okay, so one of those is in geosynchronous orbit around the moon, and then probe B rests on the surface of the moon and rotates with the moon. Okay, so we have a planet, or we have a moon, I guess we should say, and one of the probes is like right here, and then one of the other probes is out here in geosynchronous orbit. So what that means is that as one of these rotates, the other one rotates along with it. So these will always kind of be in a straight line to each other. So if they were both down here, then the object, the satellite up here, the probe, would be in a straight line with the center of mass and probe A and then probe B up here. And let's see what it wants us to do. It says rank the magnitudes of the following gravitational forces from greatest to least. If two or more quantities are the same, say so clearly. So we have to actually show that they're equal to each other. Ooh, okay, so there's a lot of stuff here. A, B, C, D, E, F. There's 6 things in total. One of them is the force of the moon on probe A. Second one is the force of the moon on probe B. All right. Let's see here. The force of the probe A on the moon and the force of probe B on the moon. Okay, those kind of sound similar to each other. And then part E says the force of probe A on probe B, and then the force of probe B on probe A. Okay, all right, so let's see if we can kind of come up with these. It says that B is on the surface of the moon, so B is right here. Moon is right here, and probe A is out in space. All right, so we need to come up with the force of the moon on probe A. That's going to be like this distance between them. Well, the force of the moon on probe A and the force of probe A on the moon, according to Newton's third law, should be exactly the same. So moon on A and A on moon, these two are going to be equal to each other. So I'm going to put like a little line right here to show that the moon on A and A on the moon, these two should be exactly the same. The same thing goes with A on B and B on A. These two things are equal to each other. So I'm going to put the square around those to show that both of those are equal to each other. And let's see, the moon and B share a Newton's third pair relationship with each other as well. Third pair, a Newton's third law pair. So the force of the moon on B, which I'll put as a star, it should be the same as the force of probe B on the moon. That's also going to be a star. So we've got three things that are equal to each other here. So we're going to need to put three equal signs. So what we really need to put here is which one is the strongest and which one is the weakest between all of these. So let's see here. It's going to depend on a lot of different things. So let's see. I think that the strongest relationship, because the mass of the moon is really, really big, and the mass of the probe, even though it's really small, there's a really close distance between these two. So I would say that the ones with the moon on B and B on the moon, so that would be B on the moon and the moon on B, the ones that are starred, those are going to be the strongest. So the greatest, we need to put B and we need to put D. And it doesn't really matter what order that we put them in, because between the two, let's put an equal sign. So that shows that B and D are equivalent or equal to each other. Now, we know that those are the greatest forces because of the distance between them, so I'm going to put a greater sign. Okay, now the next part is, let's find out what like the middle ground. Is it going to be M and A, or is it going to be A and B? Now, the difference in the distance between M and A and B are pretty close to each other. So the big difference here is going to be the mass in between them. So I would say that between A and the moon and A, that's going to be the middle, the next strongest force between them. So if you're looking at A and C, the moon on A and A on the moon, those are going to be the next ones. So I'm going to put A and C equal to each other, and that's going to be the next greatest. So the least by default is going to be E and F. Those are both going to be the weakest, and those two forces are going to be equal to each other by Newton's third law pair. So to justify your ranking, what you're going to have to do is you're going to have to justify, like, why did you set these three things equal to each other? And you know I don't like writing these out for you, because if you just write them out, then if I write them, then you'll just write them the exact same. So here's what I want you to do. In order to justify your thinking, what I need you to do is for these three things, I need you to specifically think about Newton's third law, because Newton's third law is a great way to describe how those are justification for them to be equal to each other. Okay, another thing that you have to consider between them to get a good justification of your ranking is you need to think about the distance between the two objects, and you also need to think about the masses between each other. And if you think about, ooh, I almost spelled it wrong. If you think about the masses between each body, then between these three justifications, the distances should be able to give you a reasoning between why some of these are greater than the others, and then the masses between them will give you the difference between why the mass of the moon gives you a greater pull than the mass of probe B. So that's why it has a greater pull on probe A than probe B has on probe A. And that will give you those three. Okay? Now, that was a long one, so I hope you guys learned something from it, and I hope you guys have a great day.